Well, looks like we can start. Welcome back, everyone. And sorry for the sudden cancellation of class on Thursday. That was pretty unfortunate emergency appointment with my spouse. On Friday, we had to go to the cardiac catheterization lab, as I was telling another student in class, and they didn't find any blockages. So now we're going to have to schedule up a follow-up appointment at some point. But I'm going to try to make real sure this doesn't get anywhere near actual class time. That was just a kind of unfortunate cancellation. Bit of a rocky start to the first week, but welcome back. We're essentially nearly done with the section 2.2, but we'll spend some more time on it, finishing it off. And then we're going to be moving into section 2.3. That means assignment number 2.2 is now officially scheduled. The due date will be a week away from today, since that's the day we're finishing it. But any questions at all, folks, to start us out today? Okay, well, section 2.2 is kind of a fun section. You might have noticed that there's a program that we've had linked here as well at the same time. What's kind of cool about this course is, well, really, it's just a whole bunch of interesting mathematical topics, discrete topics as opposed to what we see in calculus. But all of our major applications are to computer science. So we'll take some time to occasionally write down pseudocode to see how algorithms work. And once you write down pseudocode, the natural next thing to try to do is actually run that code. And so you can use any kind of language to make that happen. If you prefer to work with, say, C++, Python, Java, any kind of language that just feels like your first and most natural choice, that'd be a great way to take a look at how some of this pseudocode comes to life. But I found for just the sake of classroom demonstrations, R is a really, really basic language to work with. It almost looks like pseudocode itself. So it's really fast to adapt what we write down on paper as pseudocode into this language here and just show how it runs in class. So occasionally I'll run this language here through the program RStudio just to demonstrate the execution of some pseudocode. We'll do a little bit of that today just to get a preview of how that looks in section 2.2. So that's our goal today. We'll be stepping into section 2.3, working on sets as well, ending somewhere in the middle of this section, I would say. So that's the plan for the day, and pretty much how this course is going to work. Chapter 2 is kind of a interesting, get everyone all on the same page type of chapter. Chapter 3, we're going to work on formal logic. Chapter 4, we're going to be working on proofs. Chapter 5 is going to be a special kind of proofs by induction, where we'll often use pseudocode and run it in that section just to see what would something look like and how can we prove our code actually runs as intended through proof by induction. Then chapter 7, we're going to be getting into algorithms, number theory, and beyond that will be additional topics as time permits. Chapter 7, chapter 5, we're going to be running this a lot. So this is just kind of a preview of getting started to see how it all is going to go. But let's jump back in. We essentially left off on this topic right here, modular arithmetic. Well, the division or definition of modulus itself. We said initially n mod k just means the remainder you get after division of n by k. And this is what it looked like on the notes. We had a couple pretty fast problems. We know 5 goes into 17 3 times with the remainder 2. So 17 mod 5 is exactly 2. And then we had an entire formula to tie that all together. N mod k is the same as n minus k times the floor of n divided by k. And we verified that for what we saw intuitively just by looking at the problem in two pretty fast to look cases. But here is where the definition kind of goes awry. And our author, I ripped this pretty much verbatim right out of his textbook, has a lot to say about this when you see the related example in the reading as well. So I encourage you to take a look at his take on it. To boil it down, if you have a negative value here, n mod k doesn't have the same intuition like we are expecting from the actual definition of our author that he wrote out himself. And we'll come back to this when we're in chapter 7 on number theory, talking about related things like the division algorithm, modular arithmetic, and so on. But negative 13 mod 5 does have an answer. My guess is that it would be 3 or negative 3. The output of n mod k is non-negative always. We got a value of 2 when we ran it through the supplied formula, and the geometric intuition is we place negative 13 here between two multiples of 5, that number to the right of the mod operator. Negative 15 and 10 are those two multiples, and negative 13 mod 5 is just the closest distance to the nearest multiple of 5. So that's why this came out as 2 altogether. Negative 13 as it had a minimum distance of 2 to its nearest multiple of 5. Well, that's kind of the rundown of what we ended on. A week ago from today. That feels like a long time already. Any questions or comments with any of those computations? Okay, here's where we were going to finish off. Oh, there's one more. So let's do one more for the sake of practice. You know, we use the formula a lot to see how it goes, but if you saw a problem like this one, let's show how you might have done it by hand, which is perfectly fine as well in the homework. I encourage you to try out the formula a couple times, especially if you see a negative value, just to see how it goes. But if you were working at this in just step by steps, you might have said to yourself, well, 20 mod 7, 3 times 7 is 21, it exceeds 20, 2 by 7 is 14, so we have a remainder 6. So now we're just looking into 6 mod 3, and this is a perfectly fine way to compute these values as well. If you can do it in your head, then I'm not opposed to seeing this as work. How about for 6 mod 3? Anyone see the value for that one?
Would it be 0?
Yeah, absolutely. 3 goes into 6 even, remainder 0. So 6 mod 3 comes out directly as 0 on this one. So parentheses are very important to writing this out so that we can go in the way that it's intended. 20 mod 7 mod 3 just comes out as a 0 on this. Well, that's pretty much our wrap up on modular arithmetic for now. We'll come back to this quite a lot, like we mentioned in chapter 7, working in number theory and some of the related applications. But for our next big topic, we're going to be looking into summation notation. Well, you probably have already seen summation notation already. It's particular if you've taken Calculus 1, Calculus 2, this kind of stuff is all over the place in Riemann sums, series, and so on. And so there's nothing too earth-shattering here. If you did the complete reading of the textbook in chapter 2.2, then good on you. You might have noticed that it gets more involved than just this. We can have nested summations. Also, we could have products as well and nested products. But pretty much what you see in the lecture notes, like what we have up here, is going to be the extent into which we delve into the topic. Sophia says, could you explain exercise D again? Absolutely, thanks for mentioning that. So one way to look into it is that 20 mod 7 mod 3 is 6 mod 3, which equals to 0. But if we were to really break this down, here's another take on this. So look into 20 mod 7, where the claim is it should come out as a 6. Let me put a little border here so that we don't get too much visual distraction from what's above at the moment. So if we're to work this out really very carefully, one way to think of this is 6 mod 3 by the formula that's directly above turns into 6 minus 3 times the floor of 6 divided by 3. So it's kind of a nice formula because it's nested with other interesting operations we discussed in these notes. This turns into 6 mod 3 times the floor of, well, 6 divided by 3 is directly 2, and the floor of an integer is the integer itself. That just turns out to be a 2 altogether. So we would have 6 minus 6 coming out as a 0, and that's what gives us our 0 right here. I kind of did this in kind of the opposite way. I thought I was going to do 20 mod 7 first, but somehow I did the order of operations there a little bit differently. So the 0 here matches up with a 6 mod 3. I might as well just highlight that whole thing now. And if I thought about this a little bit cleaner, I probably should have started with that part first, 20 mod 7, going in the order we did the problem ourselves. So if we were to follow just ordinary order of operations, we have to obey those parentheses and do the operation of 20 mod 7 first to start out. So 20 mod 7, following the same order that we approached 6 mod 3, is the same as 20 minus 7 times the floor of 27s. So then this becomes 20 minus 7 times the floor of. This floor computation was pretty interesting, getting just a 2. And this floor operation is just as interesting as well, 27ths. Comes out as a 2.8. So what's the floor of 2.8? That's the maximum integer that you can find that's less than or equal to 2.8. So that'd be just directly a 2. We would get 20 minus 7 times 2, which becomes a 20 minus 14, giving us a value of 6 altogether. Let me retarget my highlighting here. And that's where we got the 6 right here on the very next step. Then we took 6 mod 3, ran it through this, or just thought of it intuitively. And either way we see it, we're going to get the same values. A 6 to start right here, and then a 0 as our ultimate result. Does that make sense to folks, seeing it from either point of view? Okay, well, next topic. Not too different, well, I guess it is kind of different, is summation notation. Let's take a look into this next, unless there's any further questions. Yeah, absolutely. Thanks for asking about that one. And at any point, don't hesitate to do as Sophia did, pump the brakes a little bit. Don't hesitate to interject a question over chat, over voice, and I'll be very happy to return to that. Otherwise, sometimes it can feel like we're just rushing through the notes, which is a disservice to everyone, really. So a lot of times this pace I go in class is really just informed by everyone's engagement as well. Well, summation notation, this is possibly a review for a lot of folks, but if it's brand new, then that's the purpose of section 2.2, getting everyone on the same page. The idea is we just want to add up a bunch of stuff. We're going to be looking into a finite set of integers or real numbers that we're going to add up, as opposed to calculus 2, where this could be an infinite sum. So we have a sequence of n different numbers. We write this symbol here it is as a blown up symbol, to indicate the sum of all the values, x1, x2 through xn. So this says when I is 1, take x1, the summation symbol means repeatedly add, but when we go to the next term, we update I to 2, place the term, and keep on going, so on and so forth in that kind of way. We call I the index of summation, going from 1 to n, and the things that we're actually adding together are the x1, x2, xn. The expression here will give us a formula to say, what term do you really add altogether? So here's our practice exercise on this one. The indices go from 1 to 4 for 2i. So we're adding that expression over and over again. But as I changes, the thing that we're actually adding together changes with it. So to start, index is at 1. So the expression on the inside becomes just a 2 times 1. Then we repeatedly add and update to the next index value. Here, the index is 1. We move up to an index of 2. So now we take 2 times 2, repeat, so on and so forth in that kind of way. So next is going to be 2 times, let me match the color coding, 2 times 3, plus 2 times 4 for the last term. Really, this means all we were doing with this summation is just adding the first several even numbers. Well, here it all is. We now have to compute it, but notice we ended right here because the summation is saying start at 1, but end the summation at 4. So now it's just a quick arithmetic operation. We have 2 plus 4 plus 6 plus 8. No harm just dumping that into the calculator, but this is a fast one. Looks like it comes out as 20 altogether. So that's the evaluation. Any questions or comments so far, folks, with the summation notation? Okay, should feel pretty familiar. And again, if this is our first look at it, potentially, this is really all we're doing. Changing what we see here as the variable, whatever it happens to be, then encasing the, or excuse me, separating the terms with the addition signs, and adding them straight out. But there's a lot of ways to view this kind of process. So let's take a look at this from a different point of view. Imagine you're trying to, say, code this up for an example. Throw this into a computer program and just make it do the summation for you. Maybe that's reasonable if the index up here goes all the way up to, say, 5,000, 5 million, and you have a pretty complicated expression. You wouldn't necessarily want to do this by hand to get your exact value out for the summation. So let's take a look at this from a different point of view. So to practice what this is really trying to say, the pseudocode would be by pseudocode, we mean something that we could adapt to any kind of computer language. Maybe it's R, like we're about to demonstrate in class, or maybe you have C++ or Python or something else, maybe more exotic, just ready to go. What I'm going to write down here is essentially just the algorithm to get the result. And you would know all the things that you have to include into this code to adapt it into your programming language of choice. So the code is going to start off by, well, we're adding things together. We're taking sums. So maybe the very first thing we should do is just initialize a value. Let's call it sum. Let's initialize it to a value of 0. And then that's essentially what we have had here before the 2 times 1 occurs. The sum needs to update to the very next term that we have gotten, which is going to be, plug a 0 in there, 0 minus 1. So this will update to a -1, but the index keeps increasing from a 0 to a 1, 2, 3, 4, 5, and so on. So we have to keep track of how that sum changes, much like how we were possibly doing it if you were adding this, going left to right strictly. So what we next need is a quick loop to describe this. Let's say here, for just a really fast pseudocode way to indicate a loop, I'll write for I, let's say 0 less than or equals to I, less than or equals to 5. You might write this pseudocode slightly different. Maybe it's informed by how you would have wrote this in your programming language of choice. The idea of pseudocode is this is just something that should be very recognizable to just about anyone and adaptable to any language you might pick. To organize this loop, I'm going to put a little curly brace here and say what we're doing on the very inside. Essentially, all we're doing is we're updating the sum value according to that formula that we see right here. So we might say sum is replaced with itself. We initialize it to a value of 0, so no harm done there, plus the very next value. The index I is going to start at 0, plug a 0 there, but essentially all we're putting in is I minus 1 is what's going to come in next. So after we do that repeatedly over and over again, this will close. Interpreting this to mean it's going to stop right when it gets to a 5, so I didn't say too much inside this loop. Again, you might say a lot of additional comments and statements to adapt it to your language of choice. But once we get to 5, we do this one more time, we break out of the loop, and then it would just say return that sum, whatever it happens to be. So that's the really quick, fast, and terse pseudocode that goes along with summation notation. Does that make sense to folks on that statement so far? Awesome. Well, didn't give us a value. I mean, if we want a value, there's a couple things we can do. We can just do it as a math problem, write out all these terms, add them up, get an answer out, and that's completely fine, pretty much expected in this section. But for really emphasizing what is the pseudocode doing on a line-by-line basis, there's another thing that we'll occasionally do in this course. Let's trace the execution of that pseudocode that we just wrote. We're imagining we're the computer, we're going to read this in the most hyper-literal way possible, and line by line say exactly what happens as we run through the loop, the initial value as well to start, and then when we get to the end, to return a value. So let's give this a try. Let's call just a trace of the pseudocode that we wrote down. Let's imagine what happens on a step-by-step basis. The machine is going to read this. It's going to start with the value we initialized. So step one, we're going to say the sum is 0. Nothing too earth-shattering, but on line 2, we're now trapped into the loop until the index runs through this range. So for step 2, we start updating values. I is going to be 0. We'll do this operation. We'll take sum plus I minus 1. So the sum is going to be equal to, well, this sum was the prior value that we had. It was initialized to 0, so it's going to be equal to 0 plus I minus 1 will be a 0 minus 1. And now sum has updated to a value of -1. We are still trapped in here till we get up to 5. So this is the tedious part. Maybe I should have made that a 3 or something, but let's run through it. This is our first pass through the for loop. The next thing will happen is the index I is going to update. I will be equal to 1. And we just run through this all over again in the same kind of way. Any questions or comments so far to this stage? Okay, well, we're just going to rewrite this entire statement starting right here where the red dot is. Sum is going to be equal to the prior value that we stored, which was from step 2 in the trace. It was a -1. Add to it. Remember, index I has updated to a 1, so this is just a 1 minus 1. And we get a -1 back again. Update here, index I becomes 4. Excuse me, index I becomes a 2. Don't know where I got that. Rerun whatever we set in the loop. Sum is going to be equal to prior value. This feels like deja vu, but this is progress because the index is now 2. It's updating. Plus a prior value. So plus -1. And now we've updated or output to -2. So step 5 of the trace, still in the for loop, I is now 3. Oh, let me take another look. It was 2, so this should have been a 2 minus 1. Thanks for spotting that. So this is a +1. Good eye on that. For a value of 0 altogether. Trace is really no good unless we do the arithmetic perfectly. Thanks for spotting that. So let's run through it again with the right value there, 0. Let me highlight that error in that spot and that spot as well. So index I is 3. Go through here and we'll have that sum is going to be 0 plus 3 minus 1. And now we have a value of 2 altogether. We're almost out of the loop. We're now at index I is 4. Whether we're visualizing it as the summation mathematical notation or as a for loop, we're really doing the same sort of thing. So when it's 4, we'll take sum equals its prior value of 2 plus 4 minus 1. So now we have 3 plus 2 for a value of 5. Now finally, we are updating the index to 5. So here's step 7, I equals 5. I probably really should have made that stop at 3 or something. I think we see how it goes so far. But now that the index I is 5, we can say sum, rather this one, equals prior value of the sum in step 6, so 5 plus 5 minus 1 for a value of 4, and we get a 9 altogether. Well, how's that look to folks so far? Double checking that arithmetic on that. Well, at this stage, with the index I at 5, we stop. The for loop is only valid for this range, so we break out of the loop. The last thing that's going to happen in the trace on step 8 is we return the value of sum, and currently it sits as a 9. So that would be our answer, whether we did it this way or visualized it like this. Again, there's a lot of value to seeing it like this because occasionally our algorithms get more and more involved, like in chapter 7. And also you could imagine if this was some crazy, nasty summation, maybe you work in accounting from some weird company, you wouldn't necessarily want to do it this way. You'd want to automate it this somehow, some way. Well, any last questions at all, folks? Getting through that final example. Okay, again, when you do this as a math assignment, totally fine to just do it this way. Really, I used part B just as kind of a preview of what we're going to be doing later on, particularly chapter 5's chapter and 7 as well, thinking in terms of pseudocode, tracing that code. And just for the sake of, we talked about it, let's also execute this code at the same time using R, just kind of the simplest program to bring to class that's not too notation syntax heavy, easy to work with. So if you like to use R, again, you don't have to pick the language of your choice. Here's the download link for it. We're using the language R, which is best suited to things like dealing with data, statistical computations, and those kinds of settings. There's the natural place for R. RStudio is just an integrated development environment. IDE just makes it a little bit easier to run. On this computer, it looks like this. Hit RS, and this is the RStudio application. It eventually opens. Usually this, I expect the computer to be a little faster. I don't want to open it like 5 times, but just in case I hit escape, let me try again. Okay, there it is. Might have opened it twice, but that's all right. We don't need this much of the environment, so let me kind of pare it down to what's relevant. So the idea with RStudio is I want to verify if these computations are correct in the trace and see if the pseudocode as well is going to run as intended. Very first thing I want is to click on this upper left corner to pop out a script. And this is where we're going to type out our pseudocode. And again, it's a pretty basic language. It's basically a glorified calculator in a lot of ways. If you want to initialize something, you can just write sum equals 0, and that does the job. Lots of stuff are handled internally inside of R. If we want a for loop, here's what it's going to look like for this language. For with a parenthesis, and we write for R, I in 0:5 is going to say range from 0 to 5, taking only the integer values. Curly brace organizes what goes inside the loop. Just type this in directly. Sum equals sum plus I minus 1. And the curly brace, and we're done with the loop. And in this language, I just say sum, and it will return that value. So if we run this, the hope is we get the value we trace through, which is a 9. So in this program, if you hit Control A, Control Enter, it runs everything. So here is the machine running through all those statements, actually executes the code, and sum returns a value of 9. So again, not too earth-shattering. This code here looks almost exactly like the pseudocode we put on paper. And it's a fun thing to give a try here and then. It'll become something we use more and more later on. But a couple ways to look into it. You could think of this as a pseudocode statement, trace it out. You could just do it mathematically like we did in part A. And you can check your work pretty easily if you just readapt your pseudocode like we did here. Well, that's the end of section 2.2. Any last questions or comments at all, folks, with these last topics? Okay, let me get this saved up. And like we mentioned a week ago, these get just re-uploaded with all the solutions that we have in class. So if you need a blank document, you can go here. Let me close this out. Now we're moving over to section 2.3, sets. Aside from logic, this is probably top 3 favorite topics in this course, set theory. And it's another one of those sections where you might have done a lot of set theory already. Depending on which mathematics class you've taken, you've probably been exposed to a healthy amount of it. Linear algebra in the context of vector spaces gets into set theory, for example, whether we want to or not. But just for the sake of getting everyone all on the same page, we're going to introduce set theory from scratch, looking into all the objects in a careful, calm way. So first, we're going to provide examples of sets to get started. But notice the definition. It's doesn't say much. A set is an unordered collection of objects. There's a lot that's not said here, but the very first thing it tells us is order has no meaning when it comes to sets. If order is important, we need something different, like perhaps a sequence, where the first term, second term, third term have a definite order. For sets, they don't care how you write these down. So for some really fast examples of sets, we say A equals 1, 2, 3. Then we'll have the same time. A is also equal to 3, 1, 2. Because the order is not affected by the set that we decide to write down. It's a collection of objects, so we encapsulate that collection with a curly brace to open and close around it to indicate this is a formal mathematical set. Well, that's our first set to look at. We mentioned in section 2.2 that we were looking at sets pretty much as the very first topics of the course. So other sets we've looked into are things like, say, Z positive, the set of non-negative integers. If I want to write down this collection of objects, one way to do it is to write out its 0, 1, 2, 3. But I can't actually write down this set. It has infinitely many elements inside of it. So I'll put ... to just convey it's all of these non-negative integers, and the pattern continues as we see. No skipping. 4, 5, 6 is the natural pattern, and so on is our set of integers. We've seen a lot of other sets, for example, the set C. This is a harder set to write down, but it could be pretty fast in a certain way. The set C is a collection of all objects. Z is the typical variable for a complex number, such that Z equals A plus BI, and A is in R, B is in R. So kind of a trickier set to write down. Everything has this kind of format, A plus BI, but we're referencing other sets to define the set of complex numbers in the first place. R is a set of all real numbers, the continuum, every value on the number line. So both A and B have to come from those two sets. And now we have the set C of complex numbers. Any questions so far with just these fast examples to think of the definition? Okay, here's some even weirder sets. You could have a set that goes B equals 1, and a set, say, 2, 3. So this is a set that has a set inside the set. It's not the same as a set A whatsoever. The elements of the set A are 1, 2, 3. The elements are always comma separated. But this set has just two elements. The first element is 1, and yet the second element is a set containing two elements, 2, 3. So there's lots to kind of be careful with. We have to kind of train our eyes to see when we're talking about sets. And they get even stranger because one particularly useful set is this one. Circle slash, or sometimes expressed in an equivalent way, a parenthesis with a closed parenthesis is the empty set. It's a set that contains no objects whatsoever, but we still consider that to be a set in its own right. Sometimes this is called the empty set. Occasionally people call this the null set for the same meaning. I'll often just say empty set. You can write it out this way, just a curly braces. That's kind of intuitive what's going on. It's a set with absolutely nothing in it, but usually it's written down this way. I'll usually write the empty set in that kind of way. So for yet another bizarre set, let's call the set X is the set that contains another set. That's absolutely possible. But the set I put inside the set for X is the empty set again. It's kind of weird in a certain sense. What's extra weird about this one is We throw the empty set inside the set X. The set X is non-empty because it contains one element. The empty set, which contains no elements. That seems like a kind of just weird, unnecessary thought pattern, but all this stuff is useful. It'll be helpful as we develop our way through working with sets, getting into logic. And so this is just our first look into the strange things that happen once we define something like this. There's another thing that I want to mention, which is pretty weird as well, but any questions so far, folks, with those initial examples? Okay, so maybe one last weird thing about sets to get us all kind of on the same page of thinking about these things is sets only record the unique elements. So if we write down a set, say Y, and if capital Y happens to be 1, 1, 2, 3, well, there's nothing wrong with writing that down, but this is a set that we can write down in a much, much simpler way. This is directly equal to the set 1, 2, 3. So even if you duplicate an element inside the set, mathematically, all you're really looking at is this same set. So it only shows the unique elements, even if you write down duplicates like this. And when we go to write down a set, we'll always strive to write down in this simplified form. So write in this simplified form. There's lots to talk about and discuss when it comes to sets and the weird things going along with them. So section 2.3 isn't going to get into every single kind of topic, but we'll look into just some of the starter things, the size of sets, partitions of sets. We'll look into operations like union, intersection, set difference, and so on. But we'll work into there in stages going through these notes, since if this is your first time really seeing set theory, it's a disservice to race through it. Well, any last questions, folks, before we take a look into the next example? Okay, by the way, this will never make a very good homework problem or exam problem. Usually an example like this is just our way to kind of introduce a brand new topic or a brand new definition like this one. I try to make our exercises and exam questions a little bit more directed, not so extremely wide open like this example one problem is. So next thing we want to talk about is set membership. We kind of already mentioned it, but as we were getting started, because it's hard to talk about set without saying what the elements are in that set. So set membership is defined in this way. Grab some kind of set. Usually we use uppercase letters, capital letters, like we've been indicating. Let's say we are dealing with just a set S. If there's an object X, then we write this expression, X in S, to mean X is an element of that set S. It's a statement is true if the lowercase x belongs inside the set S. So that X, weird symbol often read as just is in or element of, or is a member of, is just saying something is inside a set altogether. Well, that's pretty fast definition for set membership. And example 2 isn't major, just a way for us to practice this new definition. If we take A to be the set of all prime numbers, first of all, that's an infinite set, just like Z plus, the set of non-negative integers. There is not a finite collection of prime numbers, which is an interesting proof we could get into. It's not an easy set to enumerate. A fantastic amount of computational power for mankind as a species that's been put into trying to find as many elements of this set as possible. In particular, very, very large primes are used for computer security, cryptography. So it's a very, very important set. And this is kind of a strange question in a way. Without defining the prime numbers, anyone happen to know if this is true or false? Is 1 inside the set A?
Would it be true?
It turns out it feels true. This one's a tricky question. It turns out to be false. Again, it's a tricky problem because we didn't define prime numbers at the moment, but by a prime number, we mean a number that is only divisible by one and itself, except that one is the only exception to that particular rule. One is considered to be neither prime nor composite. So because of that small technicality, we would say one is not an element of A since one is not prime. Oh, sorry, I missed the chat. If there's a set A, if there's a set in A that's a second set, could that set be accessed by one, or do we need a prize set to search for? Well, let me think about that question, George. That's a great question. If there's a set in A that is a second set, so let me see if I'm on the right track. So we have a set A, and maybe it goes something like A, B, but there's another set and it goes 1, 2, 3. And the question is, could that set be accessed by the one, or do we need a precise set to search for? I think that kind of question you're asking on this, let me know if I'm on the right track, is we can't really get at that one. We would say one is not an element of the set A, because one is inside a set within that set. We do have, however, 1, 2, 3 as a single object is an element of the set A. And we also know 1 is an element of 1, 2, 3. But 1 itself would not be in the set A unless it's comma separate as just 1 itself, no curly braces around it whatsoever. In fact, even if it looked like this, all statements are true, except we'd have to revise this part right here. 1 is still not in the set A. It's the set that contains 1 that would be in the set A. Let me return it back to neutral. Yeah, absolutely. Other questions about that set membership so far? That's a really great question. And this is what makes set theory, especially when you're first looking at these definitions and working with it, really kind of fuzzy logic in a certain sense. We're actually going to address those particular questions quite heavily right down here. This is like a set of challenge questions. All we're going to put down is true or false next to each one of these. Some of them have to do with set membership, so that's the symbol there. Others are going to have to do with subsetting, so that's the symbol there. And these are not really easy to really investigate without taking a very, very close look at it. So that's pretty much the nature of that question as well that we're getting into already right up here. And it's another reason why in these particular notes, my sets are not going to be really big, fancy, crazy sets. They're pretty basic, like say this kind of stuff. Because learning set theory and at the same time putting in a really, really involved set at the same exact time makes it tough to pick up these definitions that we're trying to learn for potentially the very first time. But A was a particular set. It was a set of all prime numbers. Because 1 is not a prime number, we didn't say 1 is inside A. We used like the mathematical symbol for not equals. We said 1 is not an element of A. So that operation there with the slash says not an element of. Well, you might have known 43 turns out to in fact be a prime number. And you could double check this with some pretty fast computations. Take the square root of 43. There's another theorem we'll look into later on in number theory that tells us for checking for the primality of the number 43, actually we only have to test up to the square root of 43. I just need to test integers between 2 and 6. So take 43, we know 2 doesn't divide it because it's odd. 3 doesn't divide it. 4 can't since 2 didn't. 5 certainly doesn't divide it. 6 doesn't divide evenly into it. And we could keep on going all the way to the number 42. But if you test exhaustively through those numbers, you'd find nothing divides evenly. 43 is in fact a prime number. But for the problem, that means 43 is an element of the set A, the set of all prime numbers, since 43 is prime. So that's set theory so far. We know how to write down sets, how to check if an element is in a set or not. Sometimes it gets pretty complicated, so we'll look at more of these challenging kind of problems. But any questions so far with the terminology? Okay, one other comment I'd like to make is, if you like these symbols, I'd say it's terrific. It's a great shorthand, but it's pretty context sensitive. Some math books will never write this at all, and other math books like ours use it extensively all over the place. So it's more of a question of know your audience. Some people want to see that symbol. Other people would just prefer you said 43 is in A, just ordinary words. As far as your writing in class goes, I'd say pick a style, and I myself am not picky. Whether you use a symbol or if you just directly say 43 is an A, either way is good enough for me. You're saying the same thing very rigorously. Other things about sets that are interesting are their sizes. And cardinality is a really pretty deep topic that we'll potentially get into at the very end of the class. Starts out pretty tame though. The cardinality of a set S, written with these absolute value symbols, is the number of distinct elements in that set S. So, pretty fast definition. Notice it said the word distinct. So if you wrote down a set that looks like this, A equals 1, 1, 2, 3. That's a pretty weird set to write because we duplicated an element. We can simplify that set. The size of the set A is 3 because A simplified is really just 1, 2, 3. We're just counting the distinct elements inside the set A. So we'll try not to write a set more complicated that's necessary. We would not duplicate the 1, but this quick example is just to say, what is the role of that word there? Distinct. It's a tricky concept on its own as well. This set A is problematic, kind of like the question earlier above. It has 0, 1, 5 in the set 3, 2. Z is going to denote the set of all integers. So if you saw this as a problem, say, out of a math assignment, what would you all say the size of the set A is? Is it 3, 4, or 5?
I'd call that 3.
Turns out the size of this one is not 3. It's a little bit tricky though. I don't see why it wouldn't be 3 on this particular set.
I miscounted. I'd actually say 4.
Gotcha, yeah. I hear you. The commas sometimes are a little bit hard to read on that. Yeah, this has a size 4, and the gut reaction you might have is 5, but that's not the number of elements inside this set. So good call. This one has size just 4. 0 is the first element. 1 is the second element. 5 is the third element. All of the elements are comma separated. And the fourth element just happens to be weird. It's a set in of itself, but that doesn't have any bearing on this definition. We're just talking about how many objects have you thrown in there, comma separated. So this one has size 4. It means we have to read this really, really carefully, like as if we're tracing that for loop for the summation that we were writing out, because every symbol inside here is potentially important or something to watch out for. Even if it looked like this, notice the element 0 has come up twice, but it hasn't come up twice like the element 1 has come up twice. This is an entirely different element, 3, 0, compared to the element 0 as well. So it's still size 4, even if we match up one of the prior values from over here. Let me return it to what it was before. But we have another set that we're working with, Z, the set of all integers. It's the number of distinct elements, but That's undefined. There's infinitely many elements inside here. You can't say there's a million elements because we can find the million plus one element right away the moment you made that statement. So the way to write down the cardinality of this set is we would write infinity on this one, just to convey it does not have a finite number of elements. There are infinitely many elements inside that particular set. Well, that's cardinality of sets so far. Any questions about that at the moment? Okay. There's, again, lots to say about cardinality. The fact that we wrote down an infinity symbol might make you kind of uncomfortable because sets like Z, the set of all integers, or the set like R, the set of all particular real numbers, they both have infinitely many elements, but in a very real mathematical sense, the real numbers has more elements than the set of integers. The size of the infinity for the set of real numbers is bigger than this infinity. And the only way to make heads or tails of that statement is we have to work with functions that are one-to-one, functions that are onto, to get a real sense of what do we mean by the cardinality is infinity. But for the moment with where we're at on the textbook, this is the statement we would make. The size of the set is infinite if it's not a finite set. Later on, we'll have to do a little bit better to distinguish between different kinds of infinities, as weird as that sounds. Well, looks like we're already on the next topic, but any questions so far? Let's put in maybe one more. Felt like we could have put in one more statement here that would have been interesting. Let's make this a part C. Let's suppose we ask the question, what is the cardinality of the empty set? You know, I thought there was a fast way to type that out. Let's just write it this way. Let's make part C just an extra exercise on this one. What is the size of the empty set? We can put a number down on this one as well. Would you all agree that probably the most natural number should be 0? Awesome. So that's where the 0 comes in as far as cardinality is in play. If there's no elements inside the set whatsoever, let me kind of make that notation look better. We'll say the cardinality of that set is 0. Well, let's move on to the next set of interesting topics to go along with this. Better not do that. Let me put that back to where it was. Definition 2.20, we've used already. That was on our example 1, where we defined a set of complex numbers. We had to write a condition for what the element Z really was. That's A plus BI, where A is a real number and B is a real number. And for that, we were using set abstraction. This is really kind of setting the stage for the things we're going to see in chapter 3, working with logic. We'll look into so-called predicates. Predicates are statements that can either be true or false, but they depend on a value from some additional set. So let's break down this definition carefully. Let's let U be the set of all possible elements, sometimes called the universe, everything we care about, but let's go with how our author said it. No, he did say that. So called the universe. P of X is going to be a condition or predicate that for every single element inside the set U, that condition P of X is going to give us either a true statement or a false statement. So this on its own is a mathematical function. P of X is equal to true, or P of X is equal to false. And these are the Boolean values that we looked into at the very top of the section 2.2 notes. We might abbreviate these occasionally as just T or F if it makes sense, just to save some time writing. But that's what our function is going to do. So we'll have the set of all objects U coming out of the universe, uppercase U, where we do a check. P of X. If we output true, this is going to say U will then be an element of our set. We didn't give it a name. Let's give it a quick name here. Let's just say generically it's a set A. If we get a true statement, then U will be an element of that set A. If we get a false statement, then this will tell us that U is not an element. So put an angry slash through it to say not inside the set A. So this is a condition we check to determine what objects are in the set in the very first place. And for many very interesting sets, this is the best we can do if we're going to write down a set. We have to use set abstraction to say it in a very concise way. Well, we also have the definition of the empty set that we looked above on the notes as well, mainly because this comes up with set abstraction at the same time. So that's our technical definition. A is a collection of all objects U coming from a larger set, the universe, the collection of all objects that we care about, the subject of discourse, for which some statement checks as true. We're going to rewrite these sets, exhaustively listing all elements. In the set S down below for our first example, this is the statement we're going to check, the so-called predicate that we'll define later on in chapter 3. It's going to be the collection of all elements X. Well, X could be anything. X could be letters in the alphabet. It could be strings of zeros and ones, or it could be a particular kind of number. Here we're saying elements X inside the set are real numbers, such that X squared plus 1 comes out as a 0. Well, that condition's kind of tricky, right? X squared plus 1, 0, is solvable, but the solutions we get are in the complex plane. X squared plus 1 equals 0 has no solution. X in R. So if this is our predicate statement, P of X is the statement that X squared plus 1 equals 0, then P of X is always going to output false for all elements X in R. We cannot make a true statement out of that one way, shape, or form. And that means this set is empty. Nothing belongs into the set whatsoever because we can never pass this condition. Unless you change that universe R into the universe of complex numbers, then we have two solutions, negative I or positive I. So in this problem, S is simply just the empty set. We rewrote the set. We didn't exactly list them, but that's what we would get. Nothing showed up inside that set S. So that's working with set abstraction so far. Okay, we're going to come back to a lot of this kind of stuff when we're working in chapter 3 on logic. But any questions so far, folks, with that quick look at part A? Okay, looks like it would have been an interesting set. You can write down some really fantastic looking structures like this thing right here, but sometimes it's just the empty set in the first place. A lot of interesting mathematical definitions start off by saying, assume S is not the empty set, then we can define something. The other mathematical structures are just fine with the empty set coming out like it did in this case. Let's try this again, just for the sake of practice. On part B, we're looking for objects X. We have to know what they are. They have to be non-negative integers, so that's our universe U, the set of all possible elements from the definition. The predicate function is that x squared plus x minus 6 has to be directly 0, pretty similar to part A, just a different equation. So we wonder what objects belong to the set B. We'll exhaustively list its elements. Anyone happen to spot what could be in that set?
It's 3.
Yeah, absolutely. If you throw a 3 in there, that's 9 plus 3, or hang on, let me see. Is it 3? It should be. 9 plus 3 gives us 12, minus 6 gives us 6. Negative 3 does it. Yeah, so negative 3 squared is a positive 9. Negative 3 minus 6 is negative 9. So yeah, negative 3 would do the job. Or we could work it just as an ordinary algebra problem. We could say, take that equation, x squared plus x minus 6. Factor that thing down. We have x plus 3, x minus 2. This gives us two solutions. X is -3 or +2. We went this route. You have to be pretty careful though, because, well, recall we're in this set, the non-negative integers. So we can't use -3 on this one. The only value we could really use is 2. So the only solution to this one is 2 itself is the only non-negative integer in z plus that satisfies the predicate function. 2 squared plus 2 minus 6 does come out as 0 after double checking really fast. Well, those are two pretty quick examples thinking about this pretty first big definition of the course so far. Any last questions or comments at the moment? Okay, well, set theory is a pretty wild landscape. Already in set abstraction, it feels like there's lots going on, lots you can say about sets at the moment. And to really hit that topic right there, exhaustively listing its elements, here's a crazier looking set, n in z. So we want any integer that shows up, but they have to be, for the condition, two statements together. So one big predicate function, really a compound statement at this time, is we want integers between 0 and 20 such that n mod 11 equals n mod 13 and only those values. If you think what the mod function is doing, this is a pretty fast problem to solve. But if you're working on this from scratch, here's one way to do it. See if we have enough space down below. I just wasn't sure how to attack this problem. Later on in chapter 7, we'll get some tools and tricks that can help us solve a modular equation like that. That's kind of out of the scope for the moment for where we're at in the chapter. So instead, this is what I would do as a next try. Let's just break out a table and check between 0 and 20 integers n and see if they satisfy this equation. So in my table, I'll have a column n for potential elements. We'll check the left side, n mod 11. Check the right side of that equation, n mod 12, or excuse me, 13. And just see which integers have a match between the cells. It's kind of tedious, so bear with me for the moment. Let's start at 0. I think I assigned one that was pretty tedious, so this felt like a fair one to bring to class as well. On this row, if you took 0 mod 11, recall that's just the remainder after you divide 11 by 0. Well, 0 divided by 11 is 0, so n mod 11 is 0 itself. And same for n mod 13, we would get a 0 on this one. If you bump the integer to 1 mod 11, well, that's just a 1, and this is a pretty similar pattern. Really, the only way I'm getting something other than the 1 we throw in here is if we get beyond 11. So for example, (12) mod 11 comes out as 1 because 11 goes into 12 once with the remainder 1. But for anything between 0 and 10, we're just getting the input value for n itself. So the table seems kind of tedious, but it's drawn out pretty quickly. Throw a 2 here, 2 mod 11 is 2, 2 mod 13 is 2. And these are all matches, so they're going inside the set. So for 3 mod 11 is 3, 3 mod 13 is 3. Likewise, we get a 4 and a 4 here. The only changes that we get is when we exceed 11 or 13. So bear with me, let's run through this list. We'll get a 5 and a 5, a 6 and a 6 for this entry, 7 and a 7, 8 and an 8. I don't think I'm going to make it to 20 too easily, so let me see if I can get some more clean space on this. could use a table tool on the Word document, but I felt like if you were possibly doing this by hand, that's almost like cheating for class. So let's keep on going. We get a 9 and 9 here. 10, we get a 10 and 10. But now something interesting finally happens in column 2. Throw in an 11. 11 goes here, but 11 mod 11 is 0. Something new's happened. And the mod function causes a cyclic algebraic structure, which we investigate in chapter 7 and later on. The outputs to n mod 11, if we're constrained to these positive values as we see here, start at 0, they go all the way up to 10, and then it just starts to repeat. However, 11 mod 13 is still 11. We have a mismatch here. When we go to 12, we get a 1. The logic is 12 mod 11 is 1. We did it up here. Or another thought is it's just this cyclic structure starting off all over again. So if we just copy the pattern that we see, they're just going to duplicate over and over again in that same order, the same integer values. However, 12 mod 13 is still 12. For 13, we'll get a 2. On this column, 13 mod 13 is now at a 0. So this column is going to start repeating as well. And mod 13 can only output values 0 through 12. And if we increase n in this kind of way, integer by integer, those values just repeat in that exact order. So just for the sake of finishing off the table, let's keep going. We get a 3 here, a 1 here. We'll get a 4 here, a 2 here. Should try to draw a little bit smaller. For 16, we'll get a 5 and a 3. At this point, I'm not paying too much to the mod functions above whatsoever. I'm paying more attention to the structure, the order of the outputs that we get. So for 17, we get a 6, and we'll get a 4 here. Almost there. 7 and 5. 8 and 6. And last one, let's double check if this makes sense. 20 mod 11. 11 goes into 20 once, but with the remainder 9. So we're on the right track there. 20 mod 13. 13 goes into 20 once with the remainder 7. So we should have a 7 there, and it's matching the pattern. So we have equality only on elements up to 10. The moment we did 11, 11 mod 11 is 0, but 11 mod 13 comes out as a 12. That's where the very first mismatch happens. So the set H itself, because we're constrained between 0 and 20, and we are constrained by that modular equation, we were to exhaustively list the elements. We see them in the table. It goes 0, 1, 2. If you did this, dot, 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 10, I'm totally fine with that. This would just say the pattern is conveyed in the most simplest obvious way, taking all integers and writing them out. Or if you're just wanting to be really careful, let's go and follow the instructions more verbatim. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So that's the list of all elements inside that set H. The predicate function, because it had an end condition, is only satisfied for those particular values. Well, we did it, folks. Related concept you could ask yourself is, what is the cardinality of the set H? There are 11 entries inside, so it has cardinality 11. Any last questions at all running through this one? Okay, so this is set theory so far. The big definition so far was the set abstraction that we defined here, sometimes called set builder notation. The next topics we're going to take a look into when we come back on Thursday's class to finish off the notes are how to combine old sets to come up with a brand new set. So we hinted at the operation of intersection and union. We'll start with the complement of a set, look at union, intersection, set difference. As Venn diagrams, if you're a fan of those, we'll look into this. Look into set equality and subset relationships. And that's going to be the major meat of this section. And just for the sake of two interesting applications, we'll also look into partitions and power sets as well. This will be kind of like the challenge question that we're going to get into before we get into those related applications. But I think for this moment, it's going to be a rush to try to get through too many of these topics at the moment. We'll return right here when we come back on Thursday's class, talking about the complement of a set. A word of warning, the complement of a set, if you've read a lot of math books, it feels like this is defined in a different way for just about every book sometimes. Sometimes there's a superscript AC to be the complement. Other times there's a prime notation, kind of like a derivative, but it's not a derivative. For our book, we're going to say the complement of a set by using a tilde. Just another way to go. Our author likes the tilde for complement. It's one of those things in math that's just unfortunately not as standard as we would like to be from textbook to textbook. So if you do write your complements different, that's okay with me. I'll be writing it out this way just to match up the textbook. Well, any last questions or comments at all, folks, before we call it a night? Okay, well, have a great afternoon, folks. On Thursday's class, we'll finish off these notes and then move into section 2.4. Sequences are sets, but they're sets where order matters, and we'll look into other interesting related topics, vectors and matrices. But have a great afternoon, folks. We finish off section 2.2, so that first due date there is now official. This one's probably going to be about right, but I'll probably push this one back to next week, depending on where we end up. I don't like putting down 2 assignments for a single day in the first place. But I'll see you all later. If you do have questions, I'll be happy to help out. Take care. Take care. Thanks. You too.